Hello, everybody. Today we are gonna do some assignments on our final project for GIS applications for civil engineering taught by our Professor Venkatesh Dameri. We're doing the Kriging method and interpolate between the data that we received in the field of Lamar University. We collected few samples of field data, the longitude and latitudes, and the vertical elevation. We're gonna perform the ordinary kriging, and then we're gonna choose semi-variogram, the optimum semi-variogram that gives us the least error for interpolation, and then we're gonna check how the model performs, and also after that we're gonna check it with the global data sets, and we're gonna get the both method, the global model predictions and the kriging model prediction, and then see which gonna perform better and why is that. And also we're gonna plot the standard error obtained from both the kriging and global prediction, and try to justify or try to know which points we're gonna collect data on the map, such that the error gonna be changed, or place where we need more information. So let's go to the code. So this is a kriging program that is written in Jupyter Notebook. We'll be performing the ordinary kriging as well as we'll be performing the global predictions for our data points, that the field data, the raw data we did from the field experiments. For that, we're going to import all the libraries required. We're going to import the NumPy for calculating the numbers. We're going to import pandas, geopandas for the geodata frames, and we're going to also have to import the plots to plot data. We're going to use PyKrig for calculating the ordinary kriging. The package, the library is already available online, so we're going to use that. So let's dive into the code. So we're gonna, first of all, we're gonna get the directory path where all the data are located, and then we have the raw data that we collected in the field in the CSV file format. We're gonna read it. We're gonna see all the columns that are in our raw data. We can see in the x and y axis we have the coordinates, and in the z axis we have the elevation. These all are the experimental data we received. Then we're going to convert it to geodata frame to get the geometry. It's not mandatory to convert it to geodata frame. You can directly access through the CSV file, but we can also perform a geodata frame, not a big deal. Then we're going to plot it. We're going to plot the points on the surface to see how it goes, how they are scattered. So we just plotted it, and then now we're gonna use the ordinary kriging. We're gonna define the bounds for these points. These points will give us the bounds. Basically, we're gonna define the minimum and maximum x and y axis, y and z axis. So have the bounds for our contour map, or we can have the bounds for our interpolation. Then after we're gonna perform the ordinary kriging, we're gonna remove if some files are missing, or we have zero values, or the values are none. Then after we're gonna perform we're gonna evaluate the variograms model. For our field data, the variograms model shows us that the spherical model has the least errors out of all these models. So basically we're going to choose spherical model data. So we're going to utilize the spherical model, and then we're going to calculate the seal, nugget, and range, and then we're going to plot the semi-variogram, theoretical semi-variogram, and empirical data. So when we plot it, we can see this straight line that fits the curve. So it's basically supposed to have some changes here, but since we have a very small values for the range, so we don't actually see it actually how the spherical model works. But basically spherical model is hardening branch, then flattening out, and then we're gonna plot it using the ordinary Kriging as well as the global model that is basically a linear regression. So when we plot the ordinary Kriging and the global model with these results, the interpolation between two results for the same data set shows this way. So basically we can see here these 2 points are located. They are more, uh, they have lower elevation than other points because there was a ditch here uh, in our field. So we have lower elevation there, and the other parts have the similar elevation. It doesn't have a very big range because the land typically was more flat, and there was a very minimum variation with the data with the elevation. So basically specific points, the points we calculated our data had some sort of different elevation. However, all the other points are shown to be having the same elevation. The difference is basically very negligible. And when we plot the data with the global model, so what does the basic global model do? Is the linear relationship, making the least square errors between the points. So it will fit one plane or one single line in a curve that has the least square errors, that passes through all the points in the curve with the least square errors. So we can see there is a variation in contours from over here to over there. So basically what we can derive is the Kriging model predicts the or makes the contour maps much more smoother because you can see here these are the 2 points that have like higher elevations. However, here we can see only in this point the elevations are, I'm sorry, these are the 2 points that have the lower elevation, but we can see here these points have lower elevations. However, it doesn't define how well the model is over here. Then we're also going to plot the standard errors. When you see the standard errors, you can observe the range for the standard error for the Kriging is in the lower range. It performs better than the standard error over here. So we can basically derive that the ordinary Kriging better in interpolating the 0 points much more accurately and plot the contour map much more accurately than the global model. So that are the derivations we are derived. Now what we can do is it is seen that in which points we're gonna redefine the contour maps, or the point we need to get more data according to the question. I would definitely go with the points where there is higher change in the elevation. Maybe I'll go over here because this affects overall all the parameters around. So I'll go to higher steep change in elevation such that the contour maps will be much smooth. You can see it has a smoother map over here, but here the contour maps are more dense. So I will definitely go over here to find